Good to see a strong audience at 8 a.m. on a Vegas morning. Never know what you can expect at 8 a.m. Thanks for showing up. My name is Ara Ashikian. I lead the bridge development at Autodesk. And my colleague Joost from Arab, we decided to do this class together. We work together, we collaborate on a number of things. Joost is the European infrastructure BIM lead for Arab. So he brings a lot of good insight from industry in our collaboration. And just to be clear, they've been working on this multifaceted, multidimensional, interesting project for a while. So Joost is going to present many dimensions of this project. It's really cool. You'll really enjoy it. And I'm just basically parachuting in and showing a kind of a sliver of how you might tackle the complexity of this type of project using a more approachable workflow. What Joost is going to show is uber cool. What I'm going to show is slightly more direct, but we look forward to your feedback as we go through this. So curious, how many of you attended the Civil Tech Futures yesterday? Okay, great. All right, so we have quite a bit of material. I'm going to let Joost take the floor and go through this very exciting project.
Thank you. So I'm going to skip quickly through the introduction. The learning objectives for today's session, you've already read them, of course, on the website. The main topics that we're going to walk through. First, I'm going to show a couple of projects that we are working on at this time. Then I'm going to explain a little bit about the project that we are going to present during this session. I will show the challenges we faced during this project, the workflow, the Dynamo, Revit, and Civil 3D workflow, and Ara will conclude with the InfraWorks workflow. First, a little bit of information about Arab. Arab is a large international company. We have around 14,000 of employees all over the world, more than 85 offices. The projects that we, Arab Amsterdam, are currently working on and make use of the same workflow that I'm going to present today. This is the Van Brienenoord Bridge. It's the largest bridge in the Netherlands. It is located in the A16, close to Rotterdam. It's a steel arch bridge. The bridge has some steel fatigue issues, so we have to design strengthenings for the bridge. The Galekopper Bridge, another large cable stay bridge in the middle of the Netherlands. We have to widen the bridge, add a couple of highway lanes to it. We have to replace the cable stays. And again, the complete model was done using the same workflow as that we are going to present today. So this workflow does not only work for large, complex steel bridges, but also for the smaller pedestrian type bridges. The example on the screen, this is a pedestrian steel bridge. It's really complex because every element is double curved. It's created by an architect. This is impossible to model in basic plain Revit. You really need to do alignment design and scripting to be able to model this in Revit. And again, this bridge is completely modeled using the exact same workflow. Now a little bit about the project. This project was a JV between Arab and Royal Haskoning. Haskoning was responsible for the highways design, where Arab was responsible for the bridge design. The bridge is located in the A15, also close to Rotterdam. It spans a canal which is connected to the North Sea. On the top left corner you can see the current bridge, the existing one. It's a railway bridge combined with a highways bridge. Again, steel fatigue issues. So what we would have to do is to create a temporary bridge, and the temporary bridge has to last at least 25 years. So not really temporary, but still. We have to design a temporary bridge to reduce the traffic loading by about 50%. The deliverable is a BIM model, so a Revit and a Navisworks model for the market, the contractors to go and build the bridge. So we started with the design. We tried to figure out what the best shape for the bridge would be, the cheapest solution. And my colleague, Stijn, who is a parametric optimization specialist in our office, created this cool model. I hope it will play. So he created this model in Grasshopper, where he used an optimization tool to come up with the best solution for our bridge. As you can see, hopefully, on the left there's the price of the bridge in millions of euros. And this tool is optimizing the bridge. It's optimizing the cross-section properties. It's optimizing the amount of wind bracing, all the dimensions to come up with the best and cheapest solution. So as you can see, the price is being reduced. And eventually, this is the design. No, we did consider other types of bridges, like steel truss bridges, etc. But this one turned out to be the cheapest and the best solution for us. So the challenges we faced. As you might know, the Netherlands is a pretty dense country. It's one of the most dense countries in the world. The location that we have to build this bridge is really dense as well. The first problem we had to face was on the left side, there's the railway track. So we have to build this bridge on the right side of the existing highway. On the southern side, there's a dosing chamber. That dosing chamber, we are not allowed to touch it. So we have to build in a really tight space between the dosing chamber and the existing highway. This is the crossing. Crossing exists of 2 roads and 1 canal. We are not allowed to build our supports in the canal. On the northern side, there's a gas station. And at gas station, well, there's a lot of utilities underground. And as you will see later when I'm going to show the model. We also have to stay clear of the parking area of an office building. And that is the reason that the final span, the northern span of our bridge, has to be curved, double curved, if you will, because there's a spiral. And that makes this bridge a bit more complex. So because the alignment, where we have to fit it in, it's really tight and dense, our main focus at the beginning of this project was all about alignment optimization. And that is where we came up with this workflow. The workflow uses an alignment coming from Civil 3D, and the workflow looks like this. So Royal Haskoning designed the alignment in Bentley Open Roads. We imported that alignment into Civil 3D using a dynamic link. You can do that when you use data shortcuts. We scripted the Revit bridge based on the alignment and based on the whole corridor model, and we could use that to optimize the alignment. The alignment was optimized about 7 or 8 times during the project. And back in the day, when there was no scripting around, you would have to remodel the complete bridge after every alignment change. A little bit of information about the alignment. Well, it's a bit hard to see, but there's the green lines are the curves, the yellow lines are the spirals, and the blue line is the tangent. And it's especially the spiral is the tricky part, because there you have varying super elevation, which is also in our superstructure of the bridge. Vertical profiles going up and down as well, because we have to stay clear of all the clearance envelopes of the canal, the crossing roads. And this is the cross-section, or the assembly, if you will, of the deck part of the bridge. There's a couple of lanes. The blue lines on the bottom, those lines, we use those lines to lay out the floor beams of the bridge, as you will see later. It's a composite deck, so concrete combined with steel girders in this case. And all the blue crosses, also a little bit hard to see, those blue crosses, and that is the key to this workflow, they are coded. So we can retrieve those codes, the locations in this assembly, later using Dynamo. Coding of an assembly looks a bit like this. So on the left, you can see a pavement of the bridge, and all those codes on the right in the properties window, those points are coded. The handout includes a manual which is a bit more comprehensive. So if you want to apply this to your own project, please download the handout, and it's a bit more descriptive on how to apply this to your own project. The varying super elevation, a little bit hard to see, but the top profile, the top section has a cross slope of 2.5%, while the bottom one is at 5%. But as you might see, the blue line on the bottom is still at 2.5%. So the girders are staying at 2.5%, while the top of the girder is varying from 2.5% to 5%. This is the corridor model of that deck, of that superstructure assembly I've just shown. What you have to keep in mind is the denser your frequency in the sections, the more accurate your model will become. Now, the key for this workflow is to export the corridor into a data container. For this instance, I'm going to show how to use Excel for that, but you could use other options like a SQL database or Speckle. Excel works really well, but yeah, there's more options to that. What you export into the Excel are locations along the alignment combined with X, Y, Z coordinates of the cross section. And that looks like this. So the left column shows all the stations. Then you have the Y coordinates, X coordinates, Z coordinates, and finally the description is the code of your assembly, the point code. Now going to the Revit and Dynamo workflow. Before we start, a couple of appetizers. What is important to be aware of is that when you use Dynamo, the coordinate system is a little bit different than in plain Revit. So Dynamo models from the base point, while the Civil 3D coordinates are based on the survey point. They are on world coordinates. Keep that in mind. We always start all of our projects with remodeling the existing terrain, because in a dense country like the Netherlands, that's where most of your clashes come from. We started with CPTs. So a couple of the CPTs were obstructed, and we tried to figure out what the locations of those CPTs were and to show it in a model. The red arrows that you are seeing on the screen, those were the obstructed CPTs, and the concrete part that is shown on the screen was hidden underneath the ground. So this helped us to show hidden structures underneath the ground. For that, we used a Dynamo script, again based on an Excel file. This is the script. What it does, it reads the Excel file, it reads out the coordinates and the elevation of the obstructed CPT, and it places a big red arrow on top of that point at the correct elevation. Then we created the existing surface. There's multiple ways in which you can do it. You could use laser scans or topography coming out of Civil 3D. For this, we've received an Excel file with more than 300,000 points, and we used the exact same script as for the CPTs, except instead of placing big red arrows, we placed a topo surface. Since we were building next to a gas station with many underground utilities, we wanted to have them in 3D in the model as well, so that we could position our supports and our foundation piles exactly spaced along those underground utilities. And again, we use Dynamo for that. It's a really easy script. What it does, it takes a DWG out of AutoCAD with the utility lines, the pipelines, It extrudes them and clashes them with the surface, and then it projects them down at the correct elevation for each pipe type. And the end result then looks like this, 3D pipes. And this is how it looks in the existing terrain model. So as you can see, there's quite a lot of underground utilities. It's really complex.
This was modeled, it was driven by the script itself.
Yeah, exactly. Not a single part of this bridge was modeled. Everything was driven from the script. Yeah. Now, the fun part, the actual temporary bridge. When we started developing this workflow, by the way, we did not invent it. Autodesk did invent it. We only used it and optimized it and continued on that workflow. When we first started with this workflow, we created one big script to build the whole bridge, as you can see on the right. Running that script takes about 2 hours of time. So when you want to make quick changes, waiting 2 hours for each change is a no-go. So we ended up dividing the big script into a lot of smaller scripts, which you can see in the bottom left corner. And when we want to update the complete bridge, for example, after an alignment change, we have to run all those scripts in order. When we only need to update, for example, the arch of the arch bridge, we only have to open and rerun the arch script, which only takes 10 minutes or 5 minutes, for example. So when you import all the corridor points out of the Civil 3D model, it looks more or less like this in the Dynamo world. You get all those points at the exact coordinates, at the exact elevations. We used a Python script for that. The Python script is included in the handout, so if you want to recreate this, go ahead, use that Python script. We started with the grid lines for our supports so that we could connect our supports to the grid and communicate the grid lines and locations back to the highways engineer. And we used the alignment points out of the Civil 3D model to create the longitudinal grid line, and then we diverted the cross grid lines for the supports along those longitudinal grid lines. We then started with the main girders. So we extracted the main girder points out of the Civil 3D assembly, out of the Excel file, sorry. And the result was this, longitudinal girders following the highways model. And on the top right corner, if you look really well, you can see it starting to curve and spiral around. So the super elevation is varying there as well. Then the floor beams, a little bit more complex, because for the floor beams we have a maximum spacing distance. We have two curved lines, the outer lines of the bridge, so we have to take the outer curved line into account with our maximum spacing, and I will show why that is. First of all, we needed those 4 points out of the Civil 3D assembly, because on the left side that part was varying. It went from 2.5% to 5%. And those 4 points are driving the dimensions of our floor beams, of our cross girders. This is the alignment in plan view. And as you can see on the right side, there is the curve. And that is where the maximum spacing has to occur. Because in the bottom side, it's getting tighter and tighter because all the cross beams are perpendicular to the alignment. So what we did was we set out a local coordinate system along the top curve. We created planes along that local coordinate system, the orange lines. Those planes, they clash or collide with the bottom line, and that's where we created the other points. And between those points, we created the floor beams. And this is the end result. Then the arch. Arch is a little bit different because the arch, while still connected to the alignment, is basically it's a separate element. It has separate parameters. So the input for this arch was the alignment, but we had to input a lot of extra inputs like girder dimensions and arch dimensions for this one as well. And this was the result. And in this video, you can see the preliminary designs of this bridge where we were playing around with the input parameters of the arch. So I'm exaggerating a bit with the dimensions, so please bear with me, but it's easier to show it that way. That's the Excel with the corridor points. And on the left, those are all the inputs. Those inputs are the same inputs or the same parameters that our structural engineer used in the optimization script, the Grasshopper script. And I'm going to change a couple of them, like the height of the arch, the amount of wind bracing, the cross-section properties. Might take a little while, but if you look closely on the right, you should see the bridge update. So Dynamo is not really fast. Yeah, there it went. You can already see that only the arch part already takes quite a bit of time to change the parameters. Having the complete bridge in one single script takes a bit too long, unfortunately. So here I'm going to change the cross-section properties of the arch, exaggerating them a bit. But we made them varying as well. So the cross-section, the top part of the arch is thicker and wider at the top, exaggerated, and smaller at the bottom. So what you would have to realize is that the elements that are being placed in the Revit model is not just geometry, it's actual structural framing. So it's geometry you could use for example, IFC deliverables. You could add parameters to, you could read the parameters out of it. So it's intelligent geometry, not just dumb geometry. It's not a SketchUp model. The deck is a little bit different as well, because for the deck parts, we extracted the cross-section properties of the deck. And as you can see on this slide, we recreated the cross-sections of the deck so that we could extrude fluent geometry along those cross-sections. And the end result then looks like this. So on the right side, that's the cycle path. That's an FRP deck. And on the left, there's asphalt, concrete, and the shoulders with steel deck plates for the arch bridge. We also added road markings, more for the visualization models and the striping drawings in InfraWorks. Again, this is also, how to do this is also included in the handout, but basically you're using a CAD file with the stripings and extruding them on top of the deck, which is also, the striping is also double curved. Railing is a bit complex to model in Revit without the use of adaptive components. So for the railing part, we used a script that we've developed in the Netherlands. In the Netherlands we have an initiative where all the big firms are joining together to create Dutch standardized components. Those railings are included in them. You can download them for free. They're included in the handout as well, together with the script to place them. But the railing, as you can see, is built using one single script and is also double curved, following the alignment following the bridge deck. And this is the end result. So every part of this bridge is scripted in, except for the steel sheet pile walls. There was a little bit of handwork included with that, but the rest is all scripted in. Because those elements are all Revit type components, we could use the geometry to do the analysis in Sophistic, We did not do it for the whole steel bridge, unfortunately. It turned out to be a bit more or a bit too complex. And we had a time limit, but we did export all the supports into Sophistic, and that worked really, really well. So I think I have 5 more minutes left. I'm going to open the model and quickly show how the end result, what the end result looks like. So this is the Revit model. As you can see on the northern side of the bridge with all those gas pipes and electricity lines, it was quite complex to model the supports exactly in between all those pipes. As you can see, those steel pipes, highlighted in blue now, that's anchorage of the existing sheet pile wall. Again, it's a mess of free space you have to take into account there. And using this workflow, we could quickly shift, move the alignment, move the supports, update the bridge. We did not have to remodel one single object of the bridge. We only had to rerun the scripts after the alignment was updated and the whole bridge would update. So on the northern side, I hope you can see it. Here's the spiral. So it goes from 2.5% to 5%. That's about it.
Thank you. Perfect timing. Right, so it's, as we can see, it's a really interesting, complex project, all sorts of dimensions to it. Like I said at the beginning, I really am looking at a very small slice of this. And while undeniably cool, I would say that this workflow that you was presented is really kind of stemming from the fact that Revit had limitations in modeling, and there's limitations in how civil highway geometry and the bridge model have to kind of coexist in an awkward kind of dance here. There's a lot of gymnastics going on here to model. And I would also say that however undeniably cool this is, you have to be wearing probably a larger computer scientist hat than a bridge engineer hat when you're using this workflow. And what I'm going to present is how with the InfraWorks workflow, the objective is we want to make it far simpler, much more direct. Your entry ticket for the InfraWorks bridge modeling is, do I understand bridges? That's it, right? Do I know what the proportions of bridges should be like? What parameters do I want to play with? I don't want to be burdened with this heavy kind of computer science just to go to that concept. Now, there are different dimensions, and we will be introducing system-level intelligence in this workflow that goes from InfraWorks to Revit, and Dynamo will most likely be there, but not so much to drive geometry, but to look at the bridge at a higher level, at a system level. So I present, literally I spend a day or two on this, so I don't have all the knowledge of this project. I understand there's a lot of complexity for the site, there's a lot of complexity on the constraints. A lot of this you have to do anyways to figure out where you can place the bridge, where you can move it to, and so on. But really, when I put my bridge engineer hat on, I want to be directly modeling and playing with the parameters. And this is what I'm going to show here. So in the InfraWorks-led workflow, you basically say, hey, I create a model of the site. And I just link to in this case, the Civil 2D drawing that Joost provided with one of the alignments. I'm not sure which version it is. So here you have the alignment. That's it. As a bridge persona, this alignment is there. Now, what we're working on, you can make the alignment changes in InfraWorks, but what's really a key thing that we're working on now is to let the alignment change upstream, whether it's in open roads or in Civil 3D. That has to fly dynamically back to InfraWorks. And then when I put my bridge engineer hat on, I'm placing the bridge where I think it is. And then I can modify the parameters, the spacing, and so on. So the first thing I'm doing here is I'm setting kind of the pier spacings based on their drawings. And I'm just directly kind of saying, where do I want these piers to be now? I didn't go through the extra level of complexity of modeling the constraints, but you might have brought that in as well as you're placing the piers. And from that point on, as a bridge designer, I'm just saying, okay, which pier do I want here? And I'll show at the end kind of a snippet. The way you differentiate your bridge in InfraWorks from a vanilla bridge is having kind of more parametric data to play with. In this case, I modeled some of the piers. These are relatively simple piers to do an inventory. You can probably do those in 5 minutes. You make it parametric so you can change any dimension on the fly. So as a designer, you just click on it and you see all the parameters you can play with. If this pier is not to your liking, you can always create your own, right? Most engineers are just going to be in here, and on a larger team, there might be a small percentage of people that will create content, and the rest of the team is using it. Now, I'm showing what we added generic objects. You just place any parametric object on the terrain. Here, I'm just showing a snippet of sheet piling. But you could imagine adding more detail to the sheet piling and the content anchorages, whatever you think you need, and just place it, and so on in the model. Kind of rotate it, move it around. Now, these kind of intelligent objects are going to be, we just introduced these called generic objects. We're going to take them one step further so you can parent them to the pier or the foundation. As these move, they will follow. So there's the underlying component is three-dimensional with unlimited geometry, whether it's simple or complex, doesn't matter. And we're just going to elevate those in the upcoming releases to be one step smarter. So they automatically respond to bridge changes like the simpler components the bridge do. So here, I'm just using the normal InfraWorks pattern of applying. I model one pier, kind of I inherit that, apply it to the next. So really, in a few minutes, in real time, I'm designing the layout of this bridge. Now, I'm going to go over and look at kind of the complex superstructure. This is an orthotropic deck for the main arch, and then a composite approach spans. So here, this is, well, first of all, actually, we just introduced the generic objects which are going to really become smart girder systems. But in the interim, for now, in the upcoming release, you basically would kind of replace the girders with nominal, really tiny girder. What's going to happen is this generic object, if you go in InfraWorks, instead of picking individual girders, you're going to say, oh, I have a girder system, which will be what we show next. So just for a release, there's kind of this transition where you say, well, I don't really have simple girders. I'm going to bring in what we see here, a much more complex orthotropic component. So this is just from my inventor library. And you kind of, if you're creating it, might as well make it flexible. Might as well, whether you have sidewalks on each side or whether it's crowned or super elevated or orthotropic, just add those parameters. So as the designer on the right, as the engineer, I'm just going to pick the parameters that I want. Now, what's coming next is, so you can play with the super elevation. The arch is sitting kind of at the same level on both ribs. So there's a vertical offset between the floor beam and the edge girders. So you can play with all of that. That's going to be kind of more strongly linked, so the double curvature will be automatically inferred. But you can see here, you might use this in other scenarios, right? You're building in, now underneath the arch where it ties to the superstructure, you have kind of box girders. So, you know, I built that into the parametrics of the component, so I can just toggle that on in discrete locations. So you can see here, kind of that flexibility is make the component, this Lego block, as detailed as you want, and then just use it. You just place it, click on it. And if we go into kind of the ends are a bit different now. In the upcoming 2019.3, the generic objects that we introduced here, you can place them in sets, so they automatically follow the alignment. So if you have a precast segmental box girder like I showed yesterday in the tech preview, or you have this, you can quickly set them in, and then individually I can click on any instance in the set and individually change any of its parameters. So you have the benefit of working at a large scale very quickly and then zooming in and making local modifications. So it's kind of a good combination of flexibility. Now I'm going to go and select the other end, I'm just going to kind of reuse all the parameters I already set and just bring them over here. So in the workflow, we kind of make it convenient. So you inherit geometry or parametrics from one part of the bridge and bring it elsewhere. I'm adjusting the pier because of the vertical profile. I kind of lowered the dimensions there. And then I'm going to go and pick a slightly different composite box girder. And this, you'll notice at the beginning, it was kind of meant for included details for hangers and inventor and so on. I'm going to turn those off and kind of make it just a precast composite for the approach span. So I'm just playing with the parameters in here. Remove the hangers and reduce the number of floor beams. And you can see you can turn on details, whether you have field splices or shear studs. It doesn't matter, right? Add whatever you think you need. If you're going to reuse this over and over again, might as well add as much. Or maybe you start simple and in the next project you kind of refine the part. So here I'm going to use the set. Now, I only spent a day or two on this. If I were to spend longer, I would have added a bit more logic, have the option to have kind of curved and planned edge girders that follow the super elevation. All of that's possible. It's just kind of different parameters that you expose in there. So quickly, literally in real time, you're modeling the geometry. And as a bridge engineer, not as a computer scientist, I'm placing it, clicking it. Now I did the approach span on the right. I'm doing the approach span on the left. And I'm going to zoom out, and then, well, let's kind of, we can say it's not, I didn't quite get the ends right. I didn't play with the abutment too much. Now I'm going to say, well, I want to place an arch. And really at this stage, if you want to consider truss or cable stay, it doesn't matter. It's just, you're going to have that free reign of considering it. Now, at first, I said, well, I'll show different arches. I'll show one which isn't a tied arch. I'll show one which is kind of on foundations. And as a designer, you can quickly and very quickly just change the parameters, make it bigger, wider, change the rise, change the parabolic profile, the thickness, the width. And as you're doing this, the quantities will update. If this is linked to Revit, you might choose to let the Revit team know that the model's updated and so on. So there's that kind of dynamic approach to it. And here I'm switching to a tied arch, which has kind of that end detail. I'm going to kind of make the spacing compatible with the edge girders. And then I'm going to zoom in. And you could have modeled the arch with hangers in Inventor. I kind of decided to keep it separate. The advantage of keeping it separate is that you can have a whole family of hanger types that you want to consider variations. Use this arch on a different project with double hangers and so on. Here, this is where we think, for instance, well, we have, yesterday I showed you can click on the bridge and open the whole bridge in a spreadsheet and modify things at large. We're going to add a bit more intelligence so that these different components recognize the parametrics of each other, so the arch recognizes the hanger and so on. In this one, I kind of opened it up and kind of specify the hanger heights, but there's refinements coming there. Now, at some point, you're ready to go to Revit. Just click on it and say open in Revit. That's it. And in Revit, what we're working on, we've been working very closely with the Revit team on a number of fronts. The one that we're working on now is all the metadata of this bridge is passing over to Revit. Today, it's not exposed in Revit, but you need that to schedule, filter, tag, or pull out the information out of Revit. So this is coming. When you click on all these components, all the parameters are going to be available in Revit. So you can do all the back end, which is really probably the most important part of the BIM, is using that information. Here, I'm just going to quickly go in my Revit model and put a section view on the pier, on the support of the arch, just to show that. And this, again, it might be a different team. You might have the bridge team in InfraWorks, and you might have a different office with multiple people using Revit collaboration, doing rebar and all sorts of things at the same time. Now, we recently added the approach where we don't want to delay starting Revit because Revit is far more work than InfraWorks. You should start early in Revit so your drawings and production gets underway. But if things will change, the bridge is going to change while the Revit team's working on it. So this is what we introduced earlier this year. You can right-click at any time, go back to InfraWorks. I'm going to change the parameters of that foundation, make it slightly wider, lift the foundation a bit. And then I'm going to say update Revit. Don't create a new Revit model, update it. And when you update it, it has to be a change set that's really coordinated. I can put notes. Everyone knows who made the changes. Whoever's in Revit, or there's a team in Revit, whether they're using a central model or a local model, they will see this message in Revit, hey, there are changes pending from the bridge team. Do you accept them? And so on. It's really important. You can't just sneak in changes the day before the drawings are due. I move a pier and no one knew about it and every drawing updated. It has to be coordinated. So here you can see the model updated. So in most cases, if you change your parametrics in InfraWorks, the model update and your work will be preserved. So that makes it far, far more compelling. And the latter part of this video shows just going into Inventor. Inventor is a super powerful modeling tool. And it's history-based. So if you open up an Inventor model from someone else, you can go up on the left and just drag the history up, and you can kind of see the sequence of modeling. Here you can see it's just a sketch with simple extrusions. I'm going to go into slightly more complex. Now, to model in Inventor is a Cadillac modeler compared to modeling in Revit families or Adaptive. You can model directly on top of geometry. You can use all sorts of rules in there. You can use more complex geometry. So there's advantages. Once you get used to it, you'll like the Inventor workflow. Here I modeled the parabolic profile of the arch. In Inventor, I can create a sketch and place an equation of a parabolic profile. So this is what I'm going to do here. And then you can see here the sketch, the equation. So it's basically y equals cx squared. I kind of define the extents, then the geometry understands it. Again, most people don't have to do this. They're just going to say, someone on the team, hey, we need an arch. We need this super duper superstructure component. And the rest of the team is bridge people, tunnel people working in that space. But if you want to extend, we extend. You just bring it into the component library. So here you can see I'm placing these local coordinate systems that are tangent. And I can make the segment of the arch, it's curved, I can make it multi-segmented. I might have field splices or whatever. Or I can just say, for simplicity, I'm just going to have one arch segment. Every dimension can be varied here. You can have all sorts of connection details, whatever you choose to have. There's no limit there. Just model what you think you need. And if you're going to reuse it, spend a bit more time, make it more reusable in the future, more multi-purpose. So here you can see it's kind of a hollow box girder. Again, let's kind of sweep it all the way across if we want to, or create it the way I did. I had 10 segments with all the cross beams, so you can control all of that, slightly more refined approach. If you look at hangers, again, you might have a whole family collection of hangers, some with 4 cables, some with 2, some with 1, some with different brackets, et cetera, et cetera. It just becomes essentially a Lego block that you snap into place. It will play well with the rest. It will have its quantities. It will go into Revit. It will be an integral part of the parametric bridge. And finally, a quick look at orthotropic superstructure component. Really, when you decompose it, it's not that difficult to make. You have kind of floor beams and kind of sketches controlling the parametrics of the stiffeners, the floor beams. You can crown. You can add any detail you choose to add to them. And then once you have an Inventor, you just basically point to that assembly or part, and it's part of your InfraWorks catalog. So that's in the future, just have a rich catalog and reuse it. And even the catalog of components can be saved into a catalog of bridges. So you might have already a whole bunch of bridges and tunnels that become your starting point. So it's kind of a new way, a much more direct way. So, you know, Autodesk has a number of approaches. In some cases, using Dynamo makes sense. In other cases, to draw in a much larger team, you want more direct modeling, more intuitive modeling. In some cases, it's going to be a combination of both. So this project is super interesting on many levels. You showed a lot more than I did. I'm just showing how, don't worry, there's no difference in whether it's simple or complex, big or small. The InfraWorks workflow will still be the same. There's no difference, right? And in some cases, leverage scripting. In other cases, work directly. So that's it for today.
I did, but that was a while ago, more than a year ago, I guess. And the new generic objects feature functionality adds a lot more possibilities, which I could not use back then. So then in that time I failed, but right now it should get quite much further. Yeah.
So Ara, on this key to the whole thing is that parameters and pretty much data is coming across the rest. Because right now it does.
Yeah.
So you're saying that's in this update.
No, we're working on it. Not the 2019.3 doesn't have that, but all this metadata, because we had to work with the Revit team to have a new API to expose all this. And yesterday, if you were in the tech preview, I showed how when you transfer it over, when you click on these components, all the parameters show up. So this is super important for the back end that you guys would do on large projects. How do you extract this information out of the system, right? Yeah, so that's stage 2. So stage 1, where we added today, you can always go to InfraWorks and make changes, but really you want not only the parameters to be in Revit, but you also want to make at least small changes. All the quantities, volumes will come over to Revit as a shared parameter, but you still want to maybe say, I want to change the diameter of that column. So that's coming as a next step, because Revit by itself cannot resolve that. Because even if I change a pier cap, I make it 1.5 meters instead of 1 meter, there's a system effect. I might have to move the bearings, I might have to move the girders. So there's kind of this add-on that will sit on top of Revit that will kind of coordinate these changes so that it makes sense from a bridge or tunnel perspective. So that's coming up. But definitely the intention here is, in the short term, is to have all this information in Revit. So the Revit model is a full first-class model that you can do all your back-end workflows with.
Question for you, is regarding the Dynamo workflow. You mentioned that since it was getting too complex, and so much time to run it, and so you broke it up into the group of nodes individually. Was it separate file, or is it in a single file, and you had a technique of running individual segments?
It was a separate, yeah, those were separate files, but they're all still connected through the Excel file, basically. You could use Speckle, for example, which connects it. Speckle, which is an add-on onto Dynamo, which connects it online through the cloud.
Okay. That's an introduction, yes.
Yeah.
Yes.
Can you send changes to the Revit model back to InfraWorks?
The what?
Changes in Revit.
Yeah, this is what Michael was asking. This is coming a bit later next year. So first, today you can make changes to InfraWorks and push them into Revit. Now we're passing all the property sets to Revit, so those will be exposed. And then we're going to follow up to allow you to make changes there. So whether you make changes in Revit or InfraWorks, it shouldn't matter. The model's always going to be in sync in the middle, right? In the back.
Fantastic presentation. I've got a question for you. Other than the end product itself, which is the 3D model, what other benefits did this process bring? Was it faster, cheaper, better coordinated?
Yeah, it's all of that. Yeah, for us it's a lot faster. Maybe not at the beginning, but now we have all the scripts and we have the workflow. We've also written it down for other engineers to use it. It's actually faster, but I think the main thing is that it's impossible to model those complex type structures without Dynamo in Revit directly. I think that's the big one. All the double curved, for example, double curved geometry, modeling that in Revit by hand, it's like SketchUp. You're eyeballing a lot of the geometry while Dynamo is exact. You're inputting numbers. Civil 3D is exact. So Revit is really good at singular objects in the world, XYZ objects, if you will. Civil 3D is really strong in linear type geometry, and Dynamo connects the two. So yeah, it's faster, it's more precise, yeah.
You kind of compare two different processes, right? This scripting versus the
So there's a couple of things that we're working on in the InfraWorks. Once we have, what we don't have yet is making sure that the upstream road is fully dynamic with InfraWorks. So today, the road changes have to be in InfraWorks, whereas really, in reality, the highway team might be in Civil 3D or elsewhere. This is something that's coming in the next few months. And the other thing is what we talk about in Revit. We can go there, we can make changes, but really until we make the Revit fully bidirectional, there's that flexibility that this workflow offers. You might have to rerun the script, but we are not far away. When we talk next year, there'll be no limitation on geometry and detail that you cannot do in InfraWorks that you can do there. So going forward, the Autodesk position is clear. We want direct modeling and system intelligence with spreadsheets in Dynamo, but we want the engineer to be in the space and model directly, and the complexity is relevant in this workflow, right? There is no difference.
Has your team tackled anything for sections, Revit sections, cross sections for the curved geometry of the bridge? So when you have curvature, you
Yes.
cross section, you can't dimension because it's not perpendicular.
Oh yeah,
Revit
last
19.
year, yeah, Revit 19, Revit team spent a whole year essentially recreating the annotation engine to handle complex sections for complex geometry. So it used to be, had to be perpendicular. Now the sectioning, the geometry can be very complex and not at a 90-degree angle. So that was in 2019 of Revit. Because before that, the users would have to create an underlay or fake it out and fall out of BIM just to do that drawing, and now that's part of it. Jakob?
I have a question for you. With who reach errors? This is actually also a question connected to the detailing plan. So, did you use the same model to create the shop drawings, or you use this model to make the whole plan of the bridge, the geometry, and then the whole shop drawings to went other way?
So we did not yet create shop drawings for this bridge, but we did create the shop drawings for the cable stay bridge, which I've shown, which uses the same workflow. And for other types of bridges, which I did not show, but also use the same workflow. So for example, for the steel detailing, connection plates, bolts, we would model that depending on the geometry manually in a separate component, and then use Dynamo to attach it. For example, like the stiffeners, attach it to the geometry following the alignment. So that will be a combination of the two.
Okay, so you're planning to make the Dynamo script, which will automatically generate the shop drawings for the components of your bridge.
No, not automatically create shop drawings, but you could do it. There's numerous examples, probably also presented at the AU, showing that work. But we are more often involved with other phases of the project, like the planning phase, etc., and not actually the shop drawing phase. So we have not spent much time on automating that process, no. No worries.
So the shop are inside your model in Revit or in Autodesk?
No, in Revit, yeah. Yeah, definitely. We don't use AutoCAD. I don't think we even have it.
Okay, so the plans are, sorry, from my question, because it's really interesting. So the plans are actually extracted, geometry of the bridge, right?
Yes.
Like the line with the bridge.
Yeah, and like Ara just explained, in Revit 19, that has been improved immensely. Yeah. Does that answer your question?
Yeah.
Okay, great.
How do you handle profile views?
Yeah, that's a good one.
Developed elevations you're talking about? Yeah, in Revit.
Yeah, that is a workaround workflow where you export the bridge into Civil 3D, project it in the profile view. Yeah, still, yeah.
One comment I was going to make is that as you get into different types of bridges, the components can get more and more complex. And with the workflow that we're showing at InfraWorks, it doesn't matter. This is a slightly different inventor model that exposes a bunch of stuff. It becomes increasingly more awkward if you're always scripting this type of geometry, right? It's already difficult enough to do some of this to make it uber parametric with direct solid modeling. But as you get into more and more complex bridges, you want these components to be super smart, dynamic, but there's a lot of detail there, right? You have to make that easier to get to.
So in earlier part of your presentation, you showed a slide talking about double curvature of a footbridge. You're going to do a talk regarding that in this session, or I mean, not in this session, but in the future, or just as an example?
No, it's exactly the same workflow. So you could apply this workflow in the handout document to recreate.
Because you have rationalized it through the application process.
Yeah,
So that's
exactly.
very interesting for us.
Okay. Yeah, we did that in Dynamo, yeah. So it's the same workflow, and we had to rationalize it exactly for the shop drawings, yeah. So you could always send me an email about it, and I'm happy to...
We have to wrap it up, unfortunately. We're being asked to vacate.